Okay, so welcome to the next lecture on the next module on VLSI testing part of this NPTEL course. So, till now what we are discussing, we are talking mainly about different type of fault models applied to sequential circuits, then combinational circuits, sequential circuits, how to generate efficient test patterns and all those things. So, but actually if you want to club all these things, we can coin one term that is called actually offline testing. So, we can call it as offline testing. So, in this what happened? So, you had a circuit, so you applied some test pattern through an ATE and this golden response was compared. Okay, so, that is like on all the efforts, so whatever test patterns you want to apply, so that has to be determined. So, for that we have found out several algorithms like the algorithms, then we have found for sequential circuit we use what you call this time frame expansion method, and sometimes we have used the algorithm along with design for testability scheme called the scan chain, and also we have also seen how random test patterns generation can be helped to find out these test patterns. But as a whole, what was the idea? The basic idea was that the chip will be fabricated, you will put all these test patterns, match the golden response, and your job is done and you sell off in the market. But this assumption you can take, I mean if you are working say around say 90s or pre 90s kind of a thing. But as our technology or as our integration technology is becoming sophisticated and more sophisticated, we are going to deep submicron designs. So, the main another problem that arises is that once you manufacture your chip, you sell it to the market, you cannot guarantee that the chip will be okay throughout its lifetime or the expected lifetime. That means what? Some of the faults may even develop when your circuit is in operation, or it may easily develop after say 1 year or after some 6 months of operation. Now, whatever your circuit is placed is an extremely complex board. So, now if something does not work, then you have to debug that which part of the circuit is not working in a complex system like a motherboard, or you can say that the complex motherboard of your what you call the laptop or your motherboard of your mobile. So, one of the chip is not working, but as a whole you are getting some of the malfunction. So, now it is very difficult for a person or an engineer to debug by looking at by tapping the external points and debugging and finding out exactly which chip is not working, because such type of failures are very common in deep submicron designs, that individually the chips are okay, they didn't have any faults when they were being fabricated, then we sold it in the market. But after operating for some say 6 months, so that is within the lifetime, very well within the lifetime, there is some problems, and then you have to debug. So, debug takes a lot of time because you have to find out exactly which chip is wrong, then you have to replace that chip. So, and then and now the chip is already fabricated in the board, so you cannot apply the test patterns and all these things. So, there is a lot of problems in situ testing. So, the next level of testing from offline, actually this is called offline, already we discussed, all lectures till now are offline. Then there is something called in situ. In situ, that means your chip is already placed in the board and now you want to know whether still it is operating fine, because that way is the only way you can debug your circuit if something is there problem in the system. So, now but it is very difficult as it is already placed in your, like this is your motherboard and your chip is already fabricated and soldered over here. So, it is very difficult to apply test patterns and all this, because it is very difficult to get access individually to the chip, because it will be connected to some other parts of the chip. So, that will actually make your life very difficult. So, now what is the solution? So, what you can do? So, so that is the requirement of in situ testing is very much important. The important arises because of in submicron these faults which can occur even after fabrication and totally being tested to be fault free, they can occur when this system is in operation or you have deployed it. So, now on chip, that is in situ testing is a requirement for all circuits nowadays. So, that means what? That is actually called built in self test. That is what we are going to see in today's lecture. So, what it says? So, that means what? The idea is here that we have to have some arrangement in the chip or in the board that can apply some test patterns and can analyze the response and tell that this circuit is fine, that circuit is fine, and so forth. In other words, so once your circuit has been offline tested to be okay and fine using an ATE, you sell it to the market. Now, I put it on my motherboard or I put it in my system. Now, every time before my chip starts its operation, that at least before you boot your computer or before you start your advanced mobile phones, every chip will test itself. So, obviously, that testing part, what you call that test testing cannot be as exhaustive as we are doing an ATE, because ATE is a sophisticated memory with a huge memory, a sophisticated machine with a huge memory where you can, from where you can apply your patterns and where you can compare your response very efficiently and fast. But obviously if you want to make a miniature version of the ATE and you put it on chip, so what happens, every time your chip starts its operation you can test it partially, or you can say that I can apply some very important test patterns and I can get an estimate whether that circuit is working fine or not. So the debug problem becomes very easy in this case. Like for example, say there are 10 chips in your board and your circuit is not working fine, then what you can do, you can run built-in self-test, that is actually in situ testing, that is you can say that a part of the test patterns already you have used for offline testing can now be applied from another circuit which is on chip, that is a separate circuit which is used only for testing your circuit, is test pattern application and response analysis. So obviously a sub part of your test patterns will be applied in all the chips before they start their operation, and in any one of the chip you will find that the chip is not working fine. So you can very easily pinpoint that this is the chip or these are the chips where there is a problem. So that can be very easily debugged and you can pinpoint, because you do not have to, because all the chips are soldered already put in the board. So you cannot apply any external elements, external tester. So but again that is not required, but because your test pattern application circuit and test pattern analysis circuits are already in the chip. Now you can the chips this on chip testers which is actually called built-in self test, that is called built-in, that is already built in, the tester is built in the circuit. So that will respond with saying that this circuit is not working fine or this chip is not working fine. So you can easily pinpoint that chip is not working fine, you can eliminate that chip and put another chip. So your test time becomes very simple and easy for a test engineer when he is doing testing on a board level or at a system level. So that is what is the introduction to BIST. So circuits when tested are shipped to the customers with the assumption they will not fail with the expected lifetime. This was offline testing already discussed. But in modern ICs this may not hold, because even during operation the circuits may fail. To cater to this problem, we test every circuit before they start up and putting some circuits on chip. So that is actually called built-in self test. So now we will come to the basic architecture of BIST, how it works you see. So this is actually your circuit with DFT, some maybe you can, this DFT can be scan chain, etc. So some DFT is there. Now, so some normal inputs if you apply, so there is the primary inputs of your circuit. So these inputs will go via the mark. So in test mode, obviously this pin is selected, that is mode equal to 0, normal mode. So that will go to this operation and you will get primary output. So this is, you can think that this is the only small part of your circuit which is actually your normal circuit or the general circuit which is being used. Now what happens, so actually you can say that, and in the other hand other blocks you can see there are many other blocks, but that area is not very high. So when we will discuss all that, why the area is not high. So this will actually consume 99% of the area, the main circuit, and all the other parts are very small in size as we will see. So now what happens, now your circuit is now, this part is the 99% of area, that is anyway we will see later. So you see that this part of the chip is tested, this part of the chip. This part of the circuit is tested and verified fantastic fine and tested okay, and it is sold in the market after offline testing. Now it can happen that every time before you start your operation, that every time you start, so it may have some faults, or it may have some faults which is developed when the circuit is operated. Now as all these circuits are fabricated in the chips, in the board, so it is very difficult to debug where there is a problem. So you have to do in situ testing, that is even after deployment of your chips as the circuit in the boards, you want to test them. So how do you go about it? So some extra circuits will be required to do that. So one is actually called hardware test pattern generator. So what is that? So this will all actually contain your test patterns which you have determined using your D algorithm, or your D algorithm is scan chain or random test pattern generation or time frame expansion, whatever may be the case. So these are the test patterns which we have already generated. Now you have to observe that these test patterns are generally applied from an ATE. ATE is a huge expensive machine, big machine, with a lot of memory, and it is very powerful one in that sense. So but now this is your main circuit, and obviously say its area is say 1000 unit, you cannot have a 10,000 unit circuit to test it. It is infeasible and people will not appreciate that. So what you will have to do, you can only have a test pattern whose order of area may be say 10 or 100 max. If it is 1000, it cannot be even order of 100, its area should be 10. So what it approximately will do, we will see that is actually some kind of a random test pattern generation, and obviously it is very difficult to generate all the test patterns which an ATE can generate because of that memory constraint and other constraints. So you can generate very important test patterns, or in other way you can say that we are going to test the circuit for a very few most important patterns among the test patterns all generated by the algorithm, or in other words you can, another example can be some say test pattern 1 detects 10 faults, test pattern 2 detects 20 faults, test pattern 3 detects 1 fault, and so on. So you will only use those test patterns which detects more number of faults, because you are limited by the memory and hardware requirement of the test pattern generator. So you will say you use some percentage of the test patterns which you are using in the offline testing. So now when your test mode is 1, then these patterns will be applied to the circuit, but these are actually a subset of offline test patterns. So, these test patterns are actually subset of offline test patterns, and this is not equal to, this is a subset. Okay. So, this is what you do it. Now, what happens? So, a subset of them will be applied. Now, there is, now I will tell you there is a ROM. So, in the ROM what you store? You store actually whatever is the golden response or the expected response from this, for these test patterns. Now, if you can see that again, this is on chip circuit. So, this area is 1000 unit we have seen the main circuit. So, we said that we give it 10, we give it 20 kind of thing, comparator we give it 20, this can be 10. So, I mean we can say that at max we can have 10% area overhead of the general circuit. So, including all other blocks, this is say 1000 area overhead some unit, then all other test controller, this, that, for including everything you can apply only say 100 units of area. So, you can think that if I use I mean what you can say that for this for 100 test patterns, maybe there were 10,000 test patterns in the for offline testing. Now, you have got only 1000, you selected very good test patterns or efficient test pattern which detects more number of faults, and you generate with the random pattern. Then in the RAM, this ROM, if you want to store the golden response corresponding to all these 1000 test patterns, the ROM size will be very, very high. So, that you cannot do. So, exact response for these 1000 test patterns or whatever cannot be stored in the ROM. So, for what we do that? We have something called a response compactor, that is whatever response you get, we do not directly use in the comparator, we compress them. So, by compression there is something called aliasing which we will see in this lecture. So, aliasing means what? So, by compression it is a lossy compression, that sometimes because of the compression you may lose the efficiency, that is, I mean if the compression was not there you could have detected the fault, but because of the compression the detection may not be there, that is called lossy or aliasing is there present in that, but you have to compress it, because if you do not compress then the ROM size will be very, very high, and that is not possible, because I mean if you are corresponding to all the test patterns which were generated by the test pattern generator, you store the answer, what you can call the golden response in the ROM size will be very, very high, and you cannot do that. So, you have to compact it, and then for the compact response, for the compact you can have compact test pattern and output compact patterns, you can have the response in the ROM, and then you can compare with the output, that is then comparator, and if this matches then it is there. We will see all these through examples, and along with all this there is something called a test, there is something called a test controller. So, now what is a test controller? This whenever the circuit will start its operation, so you will say that start BIS, so there will be some kind of a signal, and what it will do? It will make m equal to 1, because it will select this pattern, it will ask it to generate the random patterns, it will ask it to compact the responses, as well as it will then it will also allow it, the compression will start. And whenever you say that my BIST is done, so you get the status, and now the circuit is fine, so you can go for the normal operation of the circuit. So, in that case you say that BIST is off, then controller will make m equal to 0, it will stop its operation, deactivate it, and you will deactivate this, it will also deactivate the ROM. Because one more thing you have to understand, that whenever your circuit is doing operation, so only this part of the circuit should be running, unnecessarily this one should not do its operation or should not be in execution, because then there will be a lot of power consumption. So, the test controller takes care of all this. So, whenever you want to do a BIST, you make m equal to 1, this is connected, you start operating all this, you start and get the result status. Once the BIST is done, then the test controller will make m equal to 1, and then m equal to 0 it will make. So, the normal input will go through, and all other parts of the circuits will be, BIST part will be made off. Okay. So, that is saving in this one. So, that is basically the BIST architecture. So, but here one point you have to observe, that somehow we have to make this ROM very small size and also the test pattern generator very small size, because I mean if you compare to an AT also has a hardware pattern generator and a ROM which actually analyzes the response, but AT is a very big machine with lot of memory power. So, you may not limit the number of test patterns, only the test pattern is limited by the test time, because if you are using too many test patterns then your test time will be higher, and so your AT cost will increase. But I mean from the memory requirement size and all this, there is not a much of a concern, but here is a very much concern, because it is a circuit which is put on chip, and if your main circuit is with some area restriction, some 1000 unit of area is there, nobody will allow you to use a BIST which is again having 1000 area or equivalent area of the normal circuit. So, your BIST area overhead should be very small, say around 10% or 8% or 5%, smaller the better area overhead compared to the circuit. So, that is why it is very critical to design which test patterns you have to apply and how you compact them. So, that is very important. So, that we will see slowly in our, as we proceed through our lecture. Okay. So, now So, let us see whatever we discussed. So, there is actually we have discussed the hardware test pattern generator. So, in what happens? So, this test pattern generates the patterns required to sensitize the fault and propagate the effect to the output. That is the same test patterns which we have developed in D algorithm or time frame expansion method or whatever you can call the random pattern generation. But in this case, the test pattern generator is not an equipment, it is a circuit, so its area is limited. That is why we can use only a part of them. So, storing and generating test pattern option by ATPT algorithm, this one is not feasible. Like whatever we have done by AD algorithm or time frame expansion method cannot be directly applicable. Instead, our test pattern is basically generator is what that we will see today is basically a type of a register which generates random patterns. So, it is not a specific pattern generator, like you can say that I require 0001, then 1110, then 0111, then 1111. These are the 4 patterns I require. Okay, so, for that you build a circuit. It is very difficult to do that because area overhead will be very high. So, in what we do in this case, we use something called a random test pattern generation register. So, it will generate all patterns randomly. So, you can use, and so it is a very small area overhead, as we will see. It will start generating lots of random patterns. And now, what is our duty? Our duty is that you can select that you can put a seed, as we will see, you can control the sequence of the random patterns. So, you can say that it will generate all random patterns say from 0 to the power n minus 1, generally 0 is not generated, we will see why is the case. So, like say 1 1 1 1 1 to the power n minus 1, all patterns it will generate kind of a thing, sorry 0 0 0 0 1 to the power n, all patterns it will generate. But whatever you require, so you can make the registers or this random pattern generator in such a way, so that your whatever you start generating, there is something called a seed, as we will see, which will determine what is the sequence of patterns, sequence of random patterns, but it can generate all pattern in between all 0 0 0 0 1 to the power n minus 1, that is 1 to the power n minus 1. So, and say you want pattern 0 0 0 0 1, then 1 1 1 0, then 1 1, these are the 4 patterns you want. So, you can arrange in such a way, so that in initial few runs, initial few iterations, you will get all the required 3 patterns, and then the other random patterns will be generated, but that is not required for you. So, after this 3 or 4 steps, when you get all the results, all the patterns, you can reset the circuit, and then again you can restart it whenever you require. So, but you will see that the random pattern generator will not generate only the specific 3 or 4 patterns you require, instead it will generate all random patterns from 1 to the power n minus 1. Now, we have our duty is that, or you can generate the random pattern in such a way, so that whatever patterns you require occur initially before the undesired or which you do not require for the random pattern. So, once your all the required random patterns are generated, you can reset your random pattern generator and stop the best kind of a thing. That is the basic philosophy. We will see with examples. We have also seen an input multiplexer. So, input multiplexer is nothing but it actually normal inputs to the circuit when circuit is operational and test inputs pattern when BST is executed. The control of the multiplexer is what you can call the test controller, central test controller, as we have already seen. So, it decides on the controller. So, output response compactor. So, the output response was a lossy compression, as I already told you. Why do you call it a lossy compression? Because if you are using non-compressed structure, then for all the random patterns which you are using as test patterns, the output response will have to be stored in a ROM. So, the output response for all will be very high, the large size of the ROM, and as we are very much restricted, what you can call the golden signature will be very large in that case if you are not compacting it, but similar to the test pattern generation, the output responses cannot be explicitly stored in a memory and responses cannot be compared, because it will make the ROM size very high. So, what we have to do? So, we have to compact it, so that golden signature itself becomes simpler in terms of area of the memory that stored the golden signatures. So, that is you compress it, so that whatever you have to compare will be smaller in area, size or in size, so your ROM area will be less, but it is a lossy compression. So, sometimes we will find that we are actually losing some of the test coverage because of this compression, but still you have to go about it, because you cannot have a legacy or you cannot have an ecstasy of using a huge area overhead in this case. Okay. The next element was a ROM, so which stores the golden response to be compared. Again, the golden signature here in this case is the compacted signature. So, it is a comparator. So, comparator is a comparator circuit, it is a digital bitwise comparator. So, it will compare the output response of this compressed output response of the circuit with the golden signature in the ROM. So, if it is equal, it will say yes. If there is a failure, it will say that it is a fault. And the test controller is the controller of the circuit. So, whenever the IC is powered on, if the BIS signal is made high, so this BIS procedure is started. Once the BIS status is high or low, whatever you know that if there is no fault in the circuit, then you can connect the circuit to the normal input through the mask and your circuit will start its operation. But if you find out that there is a problem in your circuit, then the BIS circuit will not allow your circuit to operate, and it will ask, it will give a message that this part of the circuit is not working in the motherboard, that is chip is not working. So, you replace the chip and then only your circuit will start operating, otherwise you cannot operate your system with a one chip faulty. So, that is another advantage of BIS, that with one or two faulty chips your circuit, your system will not start operating, so that in the end or in the middle of some operation you get a malfunction and you may lose your data and so forth. So, it will not allow your circuit or your system to boot up saying that this is a problem here, you better recover it and replace the chip and then start the operation. So, that was about the basic BIS architecture, okay, that and about the requirement and all this. So, now what we are going to see, there are two major parts of your circuit here. One is your BIS test pattern generator and another part is what? Another part is about your is a response compactor, because compactor is a digital circuit which you have already learned in a digital course. BIS controller is nothing but a controller circuit, it depends on based on requirements you have to generate some signal. So, it can be easily designed using digital circuit fundamentals and Karnaugh map or Finn-McClansky optimization. Compactor is the digital circuit. So, only two important parts which we do not know, we have to learn in the testing module is the test pattern generator, there is random test pattern generation and the response compactor and aliasing. So, these are the only two modules which we will see, other can be recollected or you can go back and look for your digital circuit fundamentals and you can do that. So, what is a random test pattern generator? So, what do you see? Say for example, if you have a circuit like this, say it has n inputs and some outputs. So, and we know that there is expected to 2n minus 1 kind of test patterns will be possible over here. We are just saying that 0 is not possible. We will see why 0 is not possible to be applied. So, let us assume that there are n inputs and the order of 2 to the power n minus 1 patterns can be possible. So, among them say you want k test patterns to be applied. Okay, so, and these k test patterns which you want to apply, which you have determined by D algorithm or time frame expansion or whatever. So, these k test patterns has to be applied to analyze the circuit for failure in the BIS. Now, what you have to do, if I generate a circuit which generates all these k patterns one by one, the area will be very large. We will see with an example. But now what we can do, the other way is that there is something very much important area is the low area overhead. So, there is some circuit actually which takes very less area overhead, which actually called pseudo exhaustive pattern generator. So, we generate at most almost all, or you can say all patterns from actually 0 is not there, means 0 is difficult to generate from 1 to 2 to the power 1. If there are n flip flops in the register, if there is a pseudo random pattern generator register is there. So, we can start from 00001 and 2 to the power n minus 1 all patterns it will generate among them, and they will be in a random fashion. So, that is actually called pseudo exhaustive and is also called random pattern, because these patterns are generated in a random way depending on your initial seed. So, initial seed means you have to load the register with some values other than all zeros, then after that you start generating the patterns in a random manner, or actually people call it pseudo random, because it will depend on the, pure, there is nothing called pure random because you depend on the seed and the connections. So, you will generate a pseudo random patterns, and among them pseudo random patterns, some of these say pseudo random patterns say 1, 2, 3, 4 something like this you will generate, and among them your k patterns will obviously be there which you need to apply to this one. And if you want to apply this in a specific order like K1, K2, K3, K4, which are among those K test patterns to be applied, you require a very sophisticated circuit, like initial pattern is say 00001, then 1111, then 00010, something like this. So, if you want to generate these 3 patterns which are your test patterns for this. So, you know that you can implement it using a using a sequential circuit, using a 3-bit 1, 2, 3, 4, using a 4-bit register and some combinational circuits you can implement it. You have to, this is your first output, then this is your next output, then this is your next output. So, you can easily go for digital circuit design with a state machine, and these are the outputs, you can do that. But then you know that you have to go for optimization of the gates and all. So, there will be some gates will be involved and the area will be very high if you have a 32-bit, if n is actually 100, 200 you know. So, if you have such a high number of bits, okay, so your area overhead of this counter or what you call test pattern generator, if you want to be deterministically, will be very high. So, what we do is that we use a pseudo exhaustive random test pattern generator. So, it will generate all random patterns between this, but whatever you do, you want to select this case k importance one from that. But now one important thing here is that, so somehow we will see intelligently you can use the starting one, so that your k inputs which are meaningful for you come as fast as possible. So, they are basically such type of registers are called linear feedback shift registers, is almost commonly used for all transient bits because it satisfies two conditions. So, LFSR, you should know the term, that is called linear feedback shift register, there is a feedback over here. So, they are used in case of bits because they generate all possible, all random pseudo random patterns, all possible in between 1s and 2 to the power n minus 1, it is pseudo random and it depends on the seed. So, by controlling the seed, you can make the register in such a way so that the patterns of importance occur first and then the patterns unnecessary to us occurs. Okay, and there are basically two type of LFSRs, we will study one by one. One is the standard LFSR and is the modular LFSR. So, we will see that, but basic idea is that they are very small in area, and secondly what? And secondly, what is the another advantage? The another advantage here is that it is a the area over it will be very small, that is one thing, and it will generate all possible patterns in a pseudo random fashion. So, you can take the whatever is required and that can be changed by using the seed. Okay. So, we will see one by one. So, there is two types, standard LFSR and modular LFSR, linear feedback shift register. So, this is the standard LFSR. So, why we call it a linear feedback shift register? Because you can see there is a lot of feedback. So, there is some feedbacks over here. Now, we will study that in a bit detail so that we can see what is basically happening. So, you see this is the register. So, there is having a D flip flops. We already told that D flip flops are generally used in this in digital circuits. So, this is D and Q. So, this is again D and Q and so forth. So, you can understand the connection. Now, what you can see is that you why you call it linear feedback shift register, because this is again D and Q. So, the output of the last flip flop you can call 0, whatever x0, this is connected to this one. Okay, so, all these pluses are nothing but XOR gates. So, a properly designed LFSR can generate a near exhaustive set of patterns. It can cycle through this one states except all zeros. A properly LFSR design is known as maximal length LFSR. We will come to that. Now, see what we are doing. So, what is the idea here? So, the output of the first flip flop or the last X0 flip flop is connected to this one, that is the feedback, and you can, and this is one H1, this is a switch actually, you can say switch or connection is there and connection not there, we will see about it. So, idea is that this Q is connected to one input of the 2 input XOR gate, and the one before flip flop or the last flip flop before the X0, the other input is in this way. Then the output of this XOR gate will be here, the output of the second last flip flop, this one will be connected to this one and so forth, and the first flip flop will have this one. So, first flip flop output input will be having a feedback from itself as well as this can be the feedback from this one. Now, there is a very important thing over here. So, this is the generic architecture of a linear feedback shift register. Why you call a feedback? Because you see this output is depending on this feedback. For this case, this or the first input of the first flip flop in that one or x minus 1 depends on the feedback of all other flip flops. But for the other cases, you see they are directly connected. This output will be here, then this output will be here, this output will control the input of the next one. So, this output will control this flip flop, this output will directly control this flip flop, dot and so forth. But the input of the first flip flop will be determined by the feedback from all other flip flops. And you can see this is a linear feedback, so it is the name the linear feedback shift register. Now, it is not mandatory that you can see there are some H's are there, H minus 1 minus 2 dot H1. So, they can be either 0 or 1. So, what do you say that if I say that H is equal to 1, that means what? This feedback flip flop, this multiply, this XOR gate will be there and this thing will be there. But if it can also be the case that we do not require a feedback from this register or this register or this register. So, if we say that we do not require a feedback from this X minus, what do you call this X1 flip flop, then what we can do is that this will not be there, H1 will be equal to 0. Okay, so, this is not there at all. This feedback is directly connected to this one if you say that H2 is equal to 1. So, your H1, H2, H3, H4 etc. can be zeros and ones. So, if it is a 1, then this feedback will be there from that flip flop, and if it is a 0, then that feedback will not be used, the other it will be a bypass of that one. So, by changing this H1, H0, H1, H2, H3 to Hn minus 1, so making them 0 and 1, you will get different types of LFSRs. Okay, so and they will have some polynomial, as we will see there is something called a characteristics polynomial for this one. So, whatever flip flop or whatever other way, so by changing this H1, H2, Hn this one having different values of zeros and ones. If it is 0, that means this XOR gate feedback is involved. If you say H1 is 1, then this flip flop is used in the feedback. If it is 0, then this flip flop is not used in the feedback. So, this will be a direct connection over here and this thing is not there. So, by using these H values to be 0 and 1, you can get different configurations of these LFSRs. So, that is what they are saying, a properly designed LFSR. Properly designed means by using a proper values of H zeros and these H values zeros and ones, you can generate a LFSR, which will generate a near exhaustive, or I can also say exhaustive test patterns, as it can cycle from 2 to the power n minus 1 states. 0 is not there. Such properties in SSR are called a maximum length LFSR. That is what we require. So, what we require? So, we require some, say, k test patterns to be generated out of this. We will see how it generates. Okay, so now if you choose properly the values, so then let us say there are n inputs. If you choose properly the values of this one, then you can generate 2 to the power n minus 1 to n bit all these patterns, 1 to 2 to the power n minus, all these patterns can be generated in a near exhaustive manner. We call near exhaustive because 0 is not included, and it will be in a random fashion. And depending on the first seed, like you initialize your registers in some values. If you have a different, I mean, like you can start with say 0, 0, 0, 1. So this can be one starting point. So this is called the seed. So using different seeds, you can get the different random, but sequence of the patterns will change, but it will cycle through to the power n minus 1 to all zeros and so forth. Or you can say it will start from your seed and it can circle. The circling length is 2 to the power n minus 1 excluding all zeros. Now this is called the maximal length LFSR because it is a full cycle, but sometimes you may not require a full cycle stuff, because you may only require k important test patterns to be generated. So using different configurations of these H1 and H0s, you can also go for it may not be a maximal length LFSR. So the cycle will be less than 2 to the power n minus 1. It will not generate all patterns in between 1 to 2 to the power n minus 1. But generally what we do is that we use a maximal length LFSR because we want all patterns to be generated, because we do not know which are the test patterns that may be required. So what we do is that we generally use a maximal length LFSR, and then we use a seed such way so that the important test patterns you require, they occur first, and then the unnecessarily test patterns will occur after those in the cycle. So once all your important test patterns are generated, you can reset your this linear feedback register. So we will see this by an example, so things will be more clear. And sometimes if you want to, if you can set this H1s and H0s, H1, 2, 3, 4, all this, if you can do it very carefully, then you can have a non-exhaustive, non-maximal length LFSR, which you can design in such a way so that only the test patterns you require are generated by this. So that is why it gives you lot of flexibility, and area overhead you can see is nothing but only some XOR gates. So and all these H will not be 1 actually, some of them will be 1 and some of them will be 0. So what is the area overhead? Some flip flops and only some of the XOR gates, nothing more than that. Why nothing more is there is required? Because even only if you want a feedback from the particular flip flop, then only the XOR gate is there, otherwise the area is not there because the XOR gate is not present. Now this whole thing can be represented by a matrix. So it is always generated by a matrix. So what is there? So you generate in a matrix, we call x t plus 1. What is the value of the register in time t plus 1 is dependent on the time present value of the matrix, this matrix, and the present input value. So x t plus 1 is equal to Ts into x t. So this is your x of t, that is the present value, and this is your next value for all the flip flops. And this is the characteristic matrix called Ts. So we will see how it can be generated. So you see, so what is the idea? So idea here is that, if you look it very if you observe it very carefully, so what is the idea? The idea output of x naught is dependent on the input of x naught is the output of x1. Similarly, the output of x n minus x, you can say that x0, x1, you can say x2, the output of x2 you can say is controlling the input of x1 and so forth. So you see what I represent, if I say that what is x0 plus 1 t plus 1, so what is x0 t plus 1 will be actually equal to what is the output of x0 t plus 1 will be the input of that is input d. So the output of x t plus 1 will be equal to actually x t this one. So whatever the value here is will be in the time period t plus 1 will be the what is the value of d at time t. Now what is the value of d at time t? It is the output of x1 at time t. So you can say that x0 of time t plus 1 is nothing but equal to x1 value of time t, because at time t the output of x1 is equal to the input of x0, and at time t plus 1 this output will come here. So this is the stuff. Similarly, it can be interpreted for all other except the first flip flop. The first flip flop depends on lot of feedbacks. So that is why if I use the matrix, so what it will find out, so you have to observe that this is nothing but a diagonal matrix is there. So this is the first column, only one bit is 1, all others are 0, this is the diagonal is only 1, and here actually you have to get the value of h1, h2 dot hn minus 1. This is the h, whether you want to have a feedback or you do not want to have a feedback. So now what is the value of x naught? t plus 1, you can easily see that is equal to 0, 0 into 0, this is equal to 0 into x 0 t plus this one with this one, that is 1 into x 1 of t plus some 0 into x 2 of t and dot dot dot, all will be 0. All these things will be eliminated and you will have only x naught t plus 1 is equal to 1 in, that is 1 you can eliminate, this is x 1 t, that is what is required. These things are eliminated because of these zeros. Now, similarly you can easily see that if I want to find out what is the value of this x 1, the x 1 of t plus 1, that is this one. So, it is actually what? So, it is actually equal to, this will be 0. So, it is a 0 factor, this one will be multiplied by this one. So, it is a 0 factor. So, this one will be have to be multiplied by this one. So, it will be 1 into x 2 of t plus all zeros will be there. So, x naught t plus 1 is equal to the x t, x 2 t, that is what. So, what is the output of this value at t plus 1? So, x 1 t plus 1, it will be equal to what? It will be x 2 t, because this value is coming here in the next log pulse. So, similarly you can find out that for all this equation holds. Now, only you have to worry about the first flip flop because it comprises the feedback. So, that we have to see once. So, this is the last flip flop, you can see over here. That you can see, this is the last feedback here. So, what is it dependent on? It is dependent on x naught, okay, and then plus if h 1 is there, then only it will be h 1 if it is whatever be the case, right. So, that x naught will be there, this one XOR with then x 1 of t kind of a thing, right. So, x 1, sorry, it will be what, sorry. The equation is something like this: input is dependent on this output XORed with this one if h 1 is a 1. Similarly, this output XORed with this output if h 2 is a 0. Similarly, this one with XORed with this one if this is 1 and so forth. If something is 0, that will not be considered. So, let us see, then again we will come back. So, x n minus 1, that is sorry x, that is last flip flop, n minus 1, this t plus 1, this one is equal to what? It is x naught t, this one is there, correct. This one is multiplied by this one plus h into x, plus is nothing but XOR. So, this one is h 1 into x 1 t plus h 2 into x 1 t dot 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 h n minus 1, then your x n minus 1 t. That means what you see, if somewhere x is 0, this h is 0, that it is not used in the feedback, then this part will be gone, it will be the only other way. Just like looking at this circuit, you can find that is the case. So, even if say we consider that all these things are 0 for this one is 0, this one is 0, this one is 0, we assume that. So, only this thing is there. So, what will be x n minus 1, x n minus 1, t 1, t plus 1, it will be nothing but x 0 of t, this we have to consider, okay, and it will be only this one is 1. So, it will be plus, it is XOR h 1, that is actually 1 now. So, you can eliminate this 1, now it is a 1. So, it is 1 dot x 1 of t. This is the case and all others are 0. So, this is the this will directly go and feedback over here. But if you want to use another over here, so you have to again put another XOR here. So, it will be again x 2 of t. So, wherever h is this h value is equal to 1, so you are using one more XOR gate. So, actually this is actually there is a very big XOR gate connected over here, and there are all the inputs coming through this one. So, whichever flip flop want to give a feedback to the first flip flop, so that h has to be made a 1 and it will be included in the equation. But if you see, if nobody wants to give the feedback, then what happens? Then only the first this feedback will be only be there and all others will not be there. So, the output of the first flip flop will be actually x naught. So, only this will remain and all others will go. That is what is being reflected by this line. So, it is x naught x n minus 1 t plus 1 is equal to first will be, that is why this is always kept at 1. So, whatever may be the case, if nobody wants to give a feedback to the first flip flop, actually last one, that is x naught, will have to give it. So, that will be there. So, x naught t will always be there and this part will depend on whether h 1 or h 2 are the zeros and ones. So, if first one wants to give a feedback, it will be 1. So, x plus are nothing but XOR. So, h 1 is 1. So, it will be 1. So, it will be there. So, this will give a feedback. feedback. So, x naught t plus x1 XOR x1 t. Then all others may not be liking to give a feedback. So, it will be all 0 and maybe this hn1 minus 1 may want to give a feedback. So, it will be another XOR, then h1 n minus 1 is 1. So, you will have x n minus 1 t. So, this is also going to give a feedback. So, this is how this matrix form also generates this or also represents this circuit. There are two representations of your what you can call your this LFSR, standard LFSR. Okay. So, now we are not going into this very depth theory, we are not going to this is a very in depth theory which is available. So, we says that then we can say just a minute. So, one more thing we will say that. So, they also it can be represented by a function. But if you have this, we can have a function representation of this one. So, how do you write it? So, we say that fx is equal to 1 is always there and xn is always there. So, if you have these are so this is the fixed, we will see how it we can easily see this how it happens. So, the LFSR there is a characteristics polynomial, we say that it is 1 and this xn minus and the last bit is xn. So, if it is the length of the flip flop is n, so there is another factor involved, that is the xn, and h1x plus h2x square plus dot dot hnx minus 1 and hx minus 1 and so forth. So, wherever you are putting h is equal to 1, so this x factor will be there and or x square will be there, and wherever it is not there, h is 0, that factor will be not there. So, this same matrix we can also represent it by a what you can call a characteristics polynomial. Then there are lot of theories. So, we will give the reference so that you can see there is some reference to find out that if what is the characteristic polynomial which can, this is the characteristic polynomial which is also defined, which can be derived from this matrix. So, if there are a lot of theories which you can check that if given this characteristics polynomial, there is something called prime characteristics polynomial, some I mean quote unquote all these things are there. So, we are not going into depth on all the theory because it will take you to a very depth analysis of this polynomial functions and all those things, or characteristic functions and all. So, I mean so some relative prime terms are there and so many other exhaustive theories there which are not going into, but given this type of characteristics polynomial, there is theory which will tell you whether this flip flop or whether this register is going to generate the exhaustive set of test patterns or not, that is whether it will cycle through 1 to the power n minus 1 or not. So, I mean if you have choose the values of h in such a way, then you can find out that characteristic polynomial is such that it will generate all possible patterns from 2 to the power n minus 1 to 1 and so forth. But there are some, if you choose the h's in different way, so the characteristic polynomial will change and then you can determine that it is not going to generate the exhaustive set of patterns, not cycle through exhaustive patterns. So, all those theories are there which can be easily determined by looking at the characteristics polynomial. So, depending on your requirement, you set the h's accordingly, and then using the theory you can easily check whether it will rotate through this what you can call the exhaustive set of test patterns or not. So, I mean this is generally the English whatever we discussed about the matrix. So, it is written that I mean depending on h1 and so forth, the flip flop may provide a feedback or may not provide a feedback. So, that is what is I explained about this matrix is written in text over there, you can go through, and but this is representation of the characteristics polynomial. So, I mean so we are not going into the theory, but by using the theory and the characteristic polynomial you can easily find out whether I mean what you can say whether it is it will go through the near exhaustive case or it will not go for the near exhaustive generation and so forth. So, we will start with an example. So, because there are a lot of theories involved in this LFSR, so better we explain with an example. So, let us see, this is a LFSR, right. So, this is x2, x1 and x0. So, this is there and you can see that this guy is not giving a feedback, only this guy is that h1 is in this case is 0 because h1 is not giving a feedback, but x0 is also must always give a feedback. So, you cannot do anything. So, this is the feedback is there. So, only h2 is 1, this guy is 0. So, no feedback is there. So, some person has designed an LFSR in this way. Now, what will be the matrix? So, you know that this is our case, this is a diagonal matrix. So, this is the case, this for this column the last bit will be 1. Why this last bit is 1? Because we always know that x0 must give a feedback to the first flip flop. So, this has to be kept as a 1 because this to generate x2 this is multiplied by this factor is multiplied by this factor. So, always we are going to get what you call the feedback. Okay. So, this one is multiplied by this one, you always keep this as a 1. So, this implies that x2 t plus 1 will be determined by x naught. This is the minimum thing that is required. Okay. So, now let us see how it represents. So, this is your this thing I mean a diagonal matrix, this is the 1, last bit is 1 and this is h1 and this is h2. h1 is 0, so you put a 0, h2 is 1, so you put a 1. So, you can easily see that what is the case. So, x naught this x naught t plus 1 is nothing but x1 product of this one. So, x naught t plus 1 is nothing but x1 t then you can say that x1t, this is nothing but this one multiplied by this one. So, x1 is nothing but x2. So, this is nothing but x2, and in the final case, that is this last one, so this one is nothing but is equal to x naught t plus this is 0. So, this will not be there, XOR with x2 t, that is what is you are getting, x2 t XOR with x naught t. So, this only determine this one. This is the case. Now, this is the matrix representation. Also, we can go for the what you can call this one, this characteristic, what do I say, you also have to go for the characteristic polynomial based LFSR representation. So, this is the case. So, you know that this thing is there. So, 3 flip-flops, so x3 cube will be there, x1 will be there. So, this one is h1 x1 plus h2 x square is there. So, h1 is 0. So, this term is not there, only this one remains, and so this is this characteristic polynomial of this LFSR, standard LFSR. Now, an important thing you have to tell that the theory is there. If you study this, you find out what is this type of a characteristic polynomial. So, it will tell you that this is the characteristic polynomial which can generate all exhaustive test patterns. So, that theory we are not going to do that, because that and there is also a list. I mean, if you look at the references, some standard references are already uploaded in this web course. I mean, in this course, you can see the site. So, there are some standard textbooks. So, the standard textbooks will give an appendix or a list of characteristic polynomial which are exhaustive in nature. So, this type of characteristic polynomial lists are available, which are proved to be in theory that will generate the exhaustive test patterns, excepting all zeros, of course. So, you can select appropriately as you want, right. So, now we will go to the example. So, in this case already that this one, that is this 1 plus x square plus x cube is already known to be generating an exhaustive test pattern case. So, that you can easily go and find out, that is in the list of the exhaustive near exhaustive and excepting zeros, all patterns it will generate. So, this characteristics is in that list of exhaustive test pattern polynomial set. So, there is a list of characteristic polynomial in which the character is that it will generate all possible patterns. So, this one falls in that can be found out in the list. So, it is expected to generate all possible patterns. Theory you can look over there. So, this is your matrix already we have seen. So, now what is requirement? Now, we have to see that it works. Yes. So, what is this? I already was mentioning that you have to give a seed. Well, the seed cannot be all 0. So, you have to give a seed. Seed means it is the starting point. So, starting point is we are giving a 1 over here. You can see x0 is 1, x1 is, say we can say that it is 0 and it is a 1. So, you can set and reset your flip flops accordingly, because by any means you can do that. So, it is done. So, you can also start with a 1 1 1 seed, that is not a problem. So, any seed you can apply. So, this seed, say for example, as I told you, say for example, for testing a circuit or so forth, very important test patterns are, say this one. So, say 1 0 0 is important, then you can say 0 1 1 is sorry. So, important test patterns are say 0 0 1, then you can say that 1 0 0, the other way. Say important test patterns are 0 0, this one, and say 1 1 1. Okay, now, so what is my duty? So, what I will see is that, so if I start with this, so this is my start point, this is seed, so this is start point. So, if this is seed, then first clock cycle this pattern is generated, one pattern is testing my faults. Next deviation I will get this, very good. So, second pattern is done. Now, this third pattern is not of requirement, not my requirement, because I mean 1 1 1 1. So, this will not test anything. So, this will go blank. Okay. Now, what happens? Now, this 1 1 1 is required and it is your 3 patterns are done. So, you can stop over here, and whenever you require again you can reset and come back. So, now there are two ways of doing it. So, once you can see the characteristic polynomial in such a way, so that it generates only this pattern, only this setup, if it is possible. It may not be always possible that it will generate only these patterns in this sequence. Then you have to solve it in a deterministic manner as you do it for a combinational circuit. So, you can try out that I want to design a sequential circuit which will generate this and this, that is only this and this. So, you will find out that it will take much more gates than a single XOR gate, it will be much higher. So, you have to do it using a Karnaugh map optimization or a Quinn-McClellan's optimization. This is the current state, then if you apply a 1, then you go here and the next state will be here and so forth. Then you go for this minimization of this is 1D, this is 1D, this is 2D, this is 3D. So, 3D flip flops are there, you have to optimize the inputs for all this. So, the standard digital circuit design, digital state machine design, you can see, we always know that in digital design that the state machine designs are there. So, you have to optimize this. So, this will be much more higher than a single XOR gate. So, if you go by that way, your circuit can design, implement, bring out this pattern and this pattern, but it will take much more number of gates than required. So, that is our constraint, that we cannot have such a huge number of gates while we are generating a test pattern generator because of the beast area override restrictions. So, what we are doing, instead we are using a this random pattern generator. So, it is very simple, as we will see, only one XOR gate is there and it is generating the near exhaustive test patterns, except in the case of 0 0 0, that cannot be generated here, because if it is there you will see that you will hang, it will always be in 0 0 0 only, but all other side is generated, and for that we require only one XOR gate. Our requirement is this one and this one. So, only we start with this seed, okay, and only we get one in sequence pasted and all others are very good for us. But if we start with this seed, then it is a problem, because this is an important requirement, you can say this is important pattern, but then again you have to get all these junk patterns there before we go back to this one. So, seed selection and characteristic polynomial selection is very good, very important. So, if you sometimes can have, based on some requirement of your test patterns, you can easily find out another characteristic polynomial which will generate only these patterns and your job is done. So, that is very good, but sometimes it may not be possible that way. So, in that case what we do, we go for the exhaustive case and then we actually put the seed in such a way so that the important patterns come first rather than the non-important patterns. So, in this case they have put the seed as 0 0 1. So, you see what is the next, so the next iteration what is going to do. So, this x0 input will control this and this one will control this in the next time. So, you know that what is going to happen. So, means x1 will go to the value of this one, sorry I wrote the wrong way. So, x1 will control this x0 and x2 will control x1 in the next iteration, and x0 with feedback will control x2. This is the cycle. So, x1 will control x0, x2 will control x1, and this x0 with all feedbacks and all will connect x2. So, this is how your matrix. So, this one will go this way, and this last bit will depend on what? It will depend on this 1 XOR with this one, because this is not involved in this one. So, 1 XOR 0 is nothing but a 1. So, this one you are going to get by XORing this x0 with x2. So, if you XOR this guy and this guy, you are going to get a 1. So, this is how the next pattern is generated. So, what is the next pattern now? So, the next pattern is 0, next pattern is now 0 0 0 and it is a 1 over here now. So, now what is the next pattern over here? You know that this one will control this one, x2 will control this one, this is the case. And now, how do you determine x2? It will depend on the XOR of 0 and XOR of 1, which is again nothing but a 1. So, this is how you get 0 0 0 1 1. So, now we are getting as 0 1 and a 1, correct. So, now again this will be the case, and now this last bit is again depending on 1, this 1 XOR 0. So, this is a 1. So, now we are going to get a 1 0 0. So, it is a 1, then x1 is 1 and this is a 0. So, similarly you can find out the next pattern will be something like this. So, 0 XOR 0 is 0, something like this. This is how this pattern will go on. And what you can find, if you can study that, just if you go by this whatever I did. So, if you can go through, you will find out that after 0 0 1, that is what x0 is 0, x1 is 1 and this is 1. So, you will get a repetition. Obviously, the repetition has to be there, this is there, this one is going to there, this one is going to there, and 1 XOR 0 is a 0, 1 XOR 1 is a 1, sorry. So, you get a 1 0 0 1 and 0 0 1 next, sorry. You are going to just see what is after that. So, it is x1 is x0 is 0, x0 is 1. After this pattern, what will be the case? And this is 1. So, you know that it will be a 0 over here, it will be a. So, what is the next pattern? We are just trying to compute what is the next pattern after 0 0 1. So, x0 is 0, x1 is a 0 and x2 is a 1 over here. So, what is the next pattern of this one? So, you know that x1 will determine this one is 0. So, it will be 0 over here. Then what is the next pattern over here? So, this is the case, and this next pattern will be, this will be a 1 over here, and this one you can determine 0 and a 1, this XOR with this one is again a 1. So, it is, and we will get again a 1 over here. So, you can see that this pattern is repeated. So, that is what I am saying. So, then again this pattern will be there and there will be lot of repetitions over there. So, what is the next, the main emphasis was that if you start with this one, so what is going to happen is that you are going to get all these patterns, and after that there is another pattern which is actually repeated. So that means what? It has, in this case it has generated 7 patterns. This is an exhaustive case. So this polynomial, as you already know that this pattern was an exhaustive pattern. So exhaustive, I mean what you can say that this polynomial was a, I mean what you can call exhaustive polynomial kind of. This characteristic polynomial was such, it will generate an exhaustive set of patterns. So it has generated all the 7 patterns starting from this seed, and after that there is a repetition 0 1 1, you can see that there is a repetition over this. So that means what? Based on this seed, it will generate this pattern and then another pattern will start occurring. So that is, after generating exhaustive pattern, one more pattern is repeating. So in this expression was what you can call is an exhaustive polynomial. So it generates all the patterns possible. So you can accordingly you can decide on the seed, and then you find that all your important patterns were up to here, and after that you can reset. So basically what we have achieved, or you can also think that my important patterns are here. So you can then start with this one as a seed and go about this way. Okay, in the very bad situation, or you can say that in the worst situation, you can have something like, so this is an important pattern, this is an important pattern, this is an important pattern, and so forth. Okay, then you have to start with another seed and see how you can achieve these patterns in a better way. So that more on that we will see in the next class. But today what was the main idea was that to show that just by using one XOR gate and changing the values of H1, H2 and H3 and so whatever, so you can generate exhaustive set of patterns. So area requirement is only one extra XOR gate, and by depending on this seed, so if you start with this seed, if you start with this one, so this will be the pattern, then that is also we can see. So you can try with different starting seeds and your patterns will be different, but again you will cycle over the exhaustive set. That is very important, that it will go around this all the exhaustive patterns. But say that if this set of patterns are important for you, they are excluding this one and so forth, so you start with this seed, so very quickly you will get this coverage, important set of test patterns, and you can stop and go around with this. Similarly, if you have some other important, say your test pattern important is this one. Okay, so this one here is also a repetition, you can see there is a repetition over here. So up to this only there is this thing, after that it repeats. Okay, so after this 1 0 0, this one was a repetition. So after that again if you apply, you will get, we got another repetition was 0 1 1. So you start repeating from this end. So 1 2 3 4 5 6 7. So after 7 there is a repetition. So this guy, so 1 0 0, this is 1 0 0, these are the repetition. So after 7th, it will always, there will be always a repetition, that you can easily see. So this is the only exhaustive part. This part is your 7 elements, 1 2 3 4 6 7. After that it gets repeated and you can say dot 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 dot, it will be repeating. So after this one we saw what was the pattern, it was 0 1 1, this was the pattern we already saw, and it will be repeating. So this whole guy will be again repeating, that already we have checked. Yes, and this one we have seen from here. So again this will be a repeating nature. So this is the block of this one. So depending on whatever is your important set, whether your important set lies over here or important set lies over here, you can choose the seed accordingly and you can do it. So another advantage is by choosing the seed properly and properly this characteristic polynomial, you can use the small area overhead pattern generator to generate the pattern of importance. But if you want to do it in a deterministic way, that is I need a circuit which will generate only these 3 and not any other, then you will be in a big problem, because you have to go for a finite state machine design of digital electronics fundamentals. So you will have to optimize the number of gates and all, so it will be much larger than a single XOR gate. So we do not have that much area flexibility or that much area overhead capability in BIST, so we have to go by this approach. We go for a linear feedback shift register, and then by choosing the seed properly, wherever is our important seed, important test patterns are there, we choose the seed accordingly and we do our job. But it is not the golden, life is not as green as this. Sometimes we may have patterns like this, 1 1 gap. Then what is the case? Then we are at a loss. Then what is the idea? Then every alternative test patterns are not of use to us. So we have to go around, test time will be larger. But if you could have designed a circuit which would only generate this test pattern, the area would have been larger, but you could have done your testing BIST faster. But anyway, we do not have that area flexibility. But then what is the solution? Sometimes you can find out some characteristics polynomial and some seed, so that it will generate only these patterns or maybe 1 or 2 more than that, but you always cannot guarantee. But that is also may be possible, which you are not looking at in this course in depth, but that also you can do as an offline study. But here but what I was emphasizing, that you have to understand that we are generating all the exhaustive patterns, and based on the seed we can generate the important patterns first, and using a very less area overhead, that is only one XOR gate. So this was about the LFSR and what is the importance in pattern generation, that is random pattern generation, and area this one. Okay, so only all zeros cannot be generated. That is very obvious. You can find out that if I put all zeros, then what is the case? So all zeros, then this one is 0 XOR 0 is again 0. So this thing will keep on generating 0. It will cannot generate anything else. So all zeros is not allowed. So this is not allowed generate. Okay, now you just think that if these are 3 input patterns. Now if we think that the inputs are 1000 in this circuit. So if you have to generate an exhaustive pattern like this, so in your BIST you require 1000 flip flops and some, in the worst case, 1000 XOR gates or even less than that. But if you want to generate a counter or a pattern generator, that is a deterministic pattern generator like a digital circuit finite state machine design, which is having 1000 flip bits, then its area overhead will be extremely high, because for each of the inputs of these flops you have to generate different combinational circuits which will generate the pivot patterns. There will be optimization and there will be at least few gates for each of the inputs of the flip flops, which will be very high in number, but in this case we require only a few number of XOR gates to do this. So with this we stop our lecture for this day, and in the next class on this module we are going to see another type of, that is standard LFSR was there. So we will see the next type of LFSR and its impact, that is called the modular LFSR. So what is the advantage and what is the disadvantage, and then we will also see about the response compaction, that why we require a response compaction, what is the advantages. So that we will be covering in the next lecture, which will complete our discussion on BIST. Thank you.